Yeah, so Daniel also co-authored the tinyML Machine Learning with TensorFlow Lite on Arduino and Ultra Low Power Microcontrollers book. He joined Edge Impulse as a founding tinyML engineer. So Daniel, over to you.
Hi, thank you so much, Wei, and thank you, Rosina. And it's a privilege to get to speak to you all today. So thanks everybody who's watching. So what I want to do today is talk to you a little bit about de-risking machine learning projects using new technologies. And the reason I want to talk about this, so I'm the founding tinyML engineer at Edge Impulse. We help a lot of embedded developers build machine learning projects. So we have over 20,000 developers, tens of thousands of projects, tens of thousands of companies where people are using our tools to design models and deploy them to embedded devices for their products that they're building. But the sad truth is, hopefully not for all of our developers, but across the industry as a whole, with machine learning and AI, 85% of AI projects are likely to deliver erroneous outcomes due to problems with data, algorithms, or bias coming in from the team that is building the project. So 85% of machine learning and AI projects are likely to essentially fail to deliver poor outcomes because of problems that happen during the process of creating a model and creating an application. So that's a huge problem, right? That's a real disaster if we think about all the time and energy and money that's put into this whole process. And so what I want to talk to you about today is how we can reduce that number and how we can make sure that that degree of successful projects is a lot higher. So the reason that's even more important for what we do with embedded machine learning is because we're dealing with resource constrained devices. So, this is a real big challenge compared to the people who are getting to run their models on big GPUs and in the cloud and servers. There's also a lack of relevant data sets because we're often working with sensors and sort of modalities of data that are not common in academia. A lot of the big common data sets that we have for more traditional non-embedded ML come out of academia, and they come out of big companies that are collecting data in certain ways, and they don't necessarily transfer over to the type of sensor data and time series data that we're often dealing with at the edge. And the third big challenge is that we have this really limited feedback loop. Once we've deployed a model to the field, potentially we don't have any feedback whatsoever. We may not have any way to measure how the model is performing or even get a sense of the distribution of outputs and inputs for the model. So three really big challenges there that amplify this problem for embedded machine learning and make it even more of a danger and even more important that we get it right. So this first problem, device constraints. So I'm going to focus on the size of models here. So often we're limited in the amount of compute we have. We're limited in the amount of memory that we have, and that limits the size of the model that we can deploy. And often the solution for that is to think about model compression. But the problem is, as this amazing research from Sarah Hooker and team showed, that when you compress a model, you can actually damage the model's performance for the long tail of examples. So if you look at this diagram here, we've got a visualization showing the number of samples that are in each sort of category of a particular data set. And you can see that most of the examples are sort of up in those first few categories. And then you have this long tail of examples which are less present in the data set. And this paper characterizing the bias of compressed models showed that when you compress a model, you start to lose performance on this long tail. So you actually have a model which stops performing well for a lot of cases. And that, it's partially an issue with the data set, but it's partially an issue with the fact that compression by nature removes information from the model. So the real thing here is that if we're trying to take conventional model architectures that are large and not really designed to be deployed to a microcontroller, we're going to have to do destructive things like compression, which results in performance that doesn't match what we'd expect. And that really hurts us when the product gets into the real world, because that's when we're going to encounter a different distribution to the distribution in the training data, and where these long tail minority examples might end up being very important. So our philosophy here to try to tackle this sort of problem is to not just rely on compression and try to compress models more and more to fit conventionally designed models into an embedded context. But instead, what we want to do is create embedded first architectures, which from the beginning are designed to suit the constraints of the situation that they're operating within. So one thing that we've done here is think about object detection. So the most common way to do object detection is using a single shot detector architecture. And it's big and complicated, it's heavy. It works well in a lot of cases, but it isn't very well suited for microcontrollers because it's essentially a big feature extractor with a bunch of extra layers on, and then some post-processing after that. So we're regressing these bounding boxes for where objects might be, and then we're doing this non-maximal suppression to find the objects that we care about and that we think are the most relevant. So what I'd like to do instead is think about what kind of use cases do we have on embedded versus the more general sort of laboratory settings that object detection models have evolved in. So in our first example here, we're looking at trying to detect objects in a very diverse and non-stationary background. So here, this model, YOLO V1, this is trained on a bunch of data which has all sorts of different backgrounds, all sorts of different objects. And it's a real big challenge and needs a really sophisticated model to be able to pick apart foreground objects from all sorts of different backgrounds. But if we think about the types of applications that we often see on MCUs, particularly in an industrial setting, we'll often have a more constrained set of scenarios. So for example, here we're looking at cubes. It could be any kind of object going down a conveyor belt, and the camera is in a fixed position always. And so that simplifies the type of model architecture we need. Even though we're doing object detection, we don't need this big and sophisticated SSD model if all we're doing is picking out regular objects that are always the same object on a regular background, which doesn't really change. And so what we've been able to do at Edge Impulse is create a much smaller, much simpler object detection model that's a little bit more akin to a pixel level segmentation model at its heart, but it's designed to work efficiently on a microcontroller, and you can get really good performance running this on a Cortex-M based device, for example. And it doesn't just work with super simple objects, even though it's designed with those in mind. You can do the same type of object detection that you can with any other SSD model, for example. The benefit is it's a lot simpler and it will fit on these resource constrained devices. So because we have this philosophy of not just trying to fit the existing architecture into a new device, we were able to go back to the drawing board and get something that works efficiently enough to run on much more constrained hardware. So the second problem I want to talk about is data sets. So data sets aren't generally very widely available for common embedded use cases. So if you think about, we're generally dealing with time series in quite specific environments, whether it's an industrial environment or consumer environment. They're often the data we care about is often stuff that there are not existing public data sets for. And this is a big challenge. So keyword spotting is something I'm going to zoom in on because this is what we've been working on in this regard most recently. But I just want to give an example of the sort of diminishing returns and the cost of data. So this is a model trained to distinguish between a couple of different words and background noise. And it's using a small subset of the Google speech commands data set. So this is around 560 samples in total in the data set, and it's class balanced. We get about 75% accuracy across all of our classes. So this is the same model trained with 10,000 samples. So this is 19 times the data, and we only get a 12% improvement in accuracy. So it shows, if you imagine the cost of collecting 10,000 samples of data, luckily we didn't have to here because it's a public data set, but in a lot of domains, there isn't public data available, for example, for the target language that you care about. So the cost and the complexity of a project massively goes up when you have to collect a big data set, but you get such a small return from collecting so much data that this is a real problem for real world embedded ML projects. So our philosophy here is that if we can reduce the data requirements, that means more people are going to be able to build successful projects. So the less data that you need, the more likely it is that projects can be successful. And so with keyword spotting context, the thing that we're doing here to follow this philosophy is developing a few shot system for keyword spotting. So based on the results that were documented in the few shot keyword spotting in any language paper by this team from Harvard University, we have built a system that allows you to take as few as 5 or 10 samples of a keyword in any language and train a model that is able to get higher accuracy than the type of model that we might train with a 10,000 keyword data set that had been collected at great expense. And the thing that's amazing there is it works across even languages that we haven't encountered before in the initial training of this transfer learning base model, the training of the embedded model. So this is just an example of a really good way to allow people to get by with less data, because it's a lot easier for a developer to come along with 5 or 10 samples and be able to create a proof of concept than to have to bring 10,000 samples and still not get very good performance. But obviously, the more data you have, the better. And it's not always going to be a great idea to just try and train your model with 5 samples, even if it is a few shot capable model. So we really encourage people to use data augmentation. But there's sort of a special flavor of that we kind of think of as data set augmentation, where rather than just augmenting individual samples during your training loop, you're actually intelligently selecting data from other data sets to bring in during training. And so the thing to remember here is that it is generally good to have more data, but not all data contributes equally to the improved performance of a model. So if we're able to select specific data based on our measurement that it seems like it will improve a model's performance, that will be a really good thing. So what we've done is build a library of data which can be used to augment keyword spotting models. And then we're selectively picking samples from that really big library of data to add to our training data set before we train a keyword spotting model. And this allows us to get massively improved performance versus just using this few shot data set. And the way we're doing this is we use representation learning to create this embedding model for our giant data set, which is, like gigabytes of data. We can then identify hard negatives from the data set, which are essentially going to be keywords which are similar to our keyword that we care about, that we're trying to train a model for, but they are actually not the same word. And so they're things that sound similar. They're things that to a model, to our embedding model look similar, but they aren't similar. And by training using a sort of judiciously selected sample of those, we're able to get a model which is more robust against that type of thing when it occurs in the field. And so another cool thing we can do is, looking at our data set, we can build a training curriculum based on the predicted difficulty of each individual sample. So we start out training with easier samples and lay a foundation, and then fine-tune the network on more difficult samples. And this ends up with better performance than if we were just doing this random mix of samples. So that's another way that you can help people make the most of the basic data they have, is by selecting data from a larger data set, but on a very specific basis. So the third and final problem I want to talk about, which to me, I think this is the most important one, is that test data set performance doesn't represent real world performance. And I think we've all seen this in practice, right? Where you train a model and it seems to work really well on your test data set, on your holdout set, but when you take it to the real world, it fails. And you really have to ask, like, what does this mean? This is a screenshot from Edge Impulse showing the performance of a model on a holdout set. And it looks like it's performing okay, right? 88% accuracy, that's not too bad. Not really enough for a production application, but maybe good for a proof of concept. But what this actually means is not that 88% of the time the model is going to match the correct keyword. It actually means that 88% of the samples in my test data set happen to be classified correctly. And to people who work in machine learning, that's kind of an obvious distinction. But to people who are just trying to get something working and just trying to build an application, and they're not necessarily a machine learning expert, it's a difficult distinction to understand. And the real issue here is that we're basically testing in a completely artificial way, where we've got these perfectly centered 1 second samples with keywords in. It's ideal circumstances. It's exactly the type of data that the model was trained on. And so you can't really trust this number as a measure of real world performance. So that causes a really big problem once you get out into the world, because once we've deployed our model into all sorts of devices, we can't necessarily get samples back of what the inputs were and what the outputs were. So where you might easily be able to test a server-side model by recording some samples of the inputs and checking manually whether they match up with what the output should be, we can't necessarily do that because of connectivity, because of energy consumption constraints and all sorts of things like that. So what we really need is to try to predict real world performance as early as possible in the feedback loop. If you've ever seen me talk before, I'm always going on about feedback loops and connecting this loop between the developer and the production deployment, or at least how the model is going to behave in the real world. Because the tighter you get the feedback loop, the more control you have over that performance, and the better you can guarantee that it will perform well. And so what we need to do is try to close that feedback loop artificially, even though we can't get that data from the real world while our device is deployed. So what we've done at Edge Impulse is build this system for realistic application testing. So the idea is that you can either generate or collect realistic samples of audio, for example, from the real world, although this would work with any type of time series data. And then you can measure the performance of your model and signal processing chain across that real world sample. And you can also evaluate in terms of industry standard metrics like false accept rate and false reject rate. And this gives you an insight into how your model's going to perform in reality that's a lot more realistic than if you were just looking at your test data set performance. And it also helps you understand the impact of post-processing. So I'm showing you on the right here is an example of a clip of audio that we've synthetically created, and we're highlighting in red the places where the model made an incorrect prediction. So it predicted a sample was the wrong keyword, for example. And what we can also then do is look at, if we're going to post-process the output of the model, how can we fine-tune the post-processing algorithm to get the best results? So once we've got a measure of real-world performance, or at least a simulation of it, we can tune the post-processing of the model to optimize the performance of the overall system in that real-world application. And so what we're able to do here is run across a sample with a bunch of different post-processing parameters. So for example, for keyword spotting, you might have an averaging window that averages the output of the model. You might have some kind of suppression period that suppresses activations after a keyword has recently been spotted. And however many of these post-processing hyperparameters exist, we can basically choose a bunch of random values and run a bunch of tests and see what is the false activation rate and false rejection rate that we get for each of these. And what we can do then is use a genetic algorithm to breed together the best results and come up with another generation. And we then do that a bunch of different times until we end up with a good number of different post-processing configurations that result in a bunch of different potential trade-offs between the false reject rate and the false accept rate. And that's what we plotted here on this graph, which is showing the Pareto frontier for FRR and FAR for this particular model. And that allows the user to pick their ideal balance between false accepts and false rejects according to their application. Because, you know, there isn't a perfect correct answer for this. And it really comes down to the application. So if you're doing something where false rejects are really dangerous, then you'll need to prioritize false activations because there's a trade-off. And so by providing this tooling that allows people to understand how their model will perform in the real world, we also allow the user to explore different configurations that apply to that and pick the best one. And so that massively helps with being able to build a system that is performing the way you expect in the real world, because we can get some real insight into how it's going to perform, and then we can calibrate the model so that it fits the exact scenario that we're designing an application for. So my conclusions here in terms of philosophy for ML projects and designing products to help machine learning developers, there's three parts. So first of all, embedded machine learning involves a lot more risk than conventional machine learning because of device constraints, because of the lack of a feedback loop, and because of the difficulty in obtaining data. But we also know that this risk can be minimized using novel approaches that people haven't had to use before because those constraints haven't existed. And so the important thing is to be really creative and try new things. See what you can come up with in terms of techniques to apply your to your models so that you can minimize the risk that creeps in embedded specific machine learning applications. So I also wanted to say we have this lucky draw, and Edge Impulse have given an Aura ring which is the next generation Aura ring. And the reason this is an amazing ring that can basically tell you how your sleep quality is and help you understand how to get better sleep. And the reason we're giving this away is the team at Aura actually use Edge Impulse to help build the product. So we're really proud of this because it's a really amazing product and it shows the power of the embedded machine learning technology. So that's it from me, unless you have any questions. I'd also like to point out that we are currently hiring. So if you're interested in working with our amazing team, please just drop me an email. You can reach us at hello@edgeimpulse.com. So really love to hear from you, whether you're interested in joining us or if you just have any questions about our platform. So thank you very much. And yeah, I'd love to answer any questions.
Hi, Daniel, Evgeny here. Great presentation as usual. I may have missed one point you made. You said that compression makes bias worse, which I get. And then you said that by moving to tinyML, this kind of problems becomes less. So that's kind of the connection I missed. I think at the end of the day, it's still the bias is still dependent on the data, right? What kind of data you have, not so much if it's tiny or not tiny.
So yeah, that's a good question. So the point from the beginning of the talk, let me zoom back there, is that we have this problem where you can get essentially end up with a biased model,
right?
Not necessarily because the data set is biased. You can still, with an unbalanced data set in terms of these subclasses, end up with a model that works well. The problem is when you compress the model. So for example, you might use quantization. You're throwing away some of the information that represents this long tail of subclasses. And so when you apply compression, that's when you get the issue. And so the solution there is, rather than taking a model which works at a sort of large scale and shrinking it down by compressing it, we should start by taking an architecture that is better suited to an embedded target, for a resource constrained target. So if we're talking about models for vision, for example, so we might try and train an image classifier, and we have a choice between different architectures, and some architectures work better at a reduced parameter count, and it's generally going to be better to pick one of those rather than try to start with a larger parameter count and reduce the size of the model using compression.
I think I got it now. So let me rephrase it, Daniel. What you're saying is that if you have a good data set, like very well balanced data set, and if you train a big model, it works well, no bias there. You compress it, you saw the bias. What you're saying is, instead of doing this, you develop a tiny model, use the same kind of balanced data set, and then you don't need to compress. That's why you don't then use bias. That's
and you might not need to do as much compression. You essentially, if you're smart about using an architecture that's well suited to the context, then maybe you don't need to do some of these destructive things that can result in poor performance in the real world.
Thank you, Daniel.
Yeah, thank you, Evgeny.
I have one question from the audience. Not sure, Daniel, if you're able to see this. So the question is, are there any heuristic specific research, either by Edge Impulse or others, machine learning developer can use to de-risk the compromised performance of a compressed model on an embedded system?
Yeah, thank you, Mark, and good to hear from you. But I think a really good resource for this is the paper referenced in this slide, which is characterizing the bias of compressed models. It's really good, and it does talk through a toolkit that is helpful for evaluating this type of thing. So really, really helpful. And just sort of as a general rule of thumb, it's good to think about your data set in terms of not just the the classes that maybe you care about at an application level, but to try to drill down into your data set in the same way that has been done here, where we are essentially looking at the subgroups that make up the data set instead of just the overall classes that we care about for our particular application, and make sure that we're not losing performance for those subgroups, especially the ones that are low frequency.
Okay, thank you. Thank you, Daniel, for the wonderful presentation. I also want to extend our gratitude to all the tinyML strategic sponsors who made this event possible. At the executive sponsorship level, we have ARM, my old employer, who provides the software and the hardware foundation, tinyML. Edge Impulse is the tinyML platform for all developers. Qualcomm advances AI research to make efficient AI ubiquitous. Sentient offers end-to-end deep learning solutions for tinyML and Edge AI. At the Platinum sponsorship level, we have Reality AI adds advanced sensing to your product with Edge AI and tinyML. Renesas, who has big ideas for every space. With our golden sponsors, Latent AI develops adaptive AI for the intelligent edge. Maxim Integrated, who is now part of Analog Devices, enables edge intelligence. Seed Studio, they are the IoT hardware enabler. tinyML builds smart IoT sensor devices from data. SynSense builds sensing and inference hardware for ultra-low power devices. We will have some special partner sessions in the next few days, led by the sponsors we just introduced. At the silver sponsors level, we have Aeon Devices, Deep Light, AMSA Vision Sense, GreenWaves Technology, Gravity, HOTG, Imagine Mob, Kixel, Rexin, and SAP.